You're on the highway, traffic slows, the car in front of you brakes, and you ease off the accelerator. And that's when you catch it, the temperature needle. It's not where it usually sits. It's drifted quietly toward the right, toward the red. Most drivers feel a jolt of panic. They pull over, they wait, maybe they call for help. Maybe they pour a bottle of water somewhere under the hood and hope for the best. But almost nobody stops to ask the actual question, what is happening inside that engine right now? Because here's what they don't tell you. By the time you see steam, the damage may already be done. And it didn't start with a catastrophic failure. It started with a single degree. Here's the misconception almost every driver carries. Overheating is a moment. The car gets too hot, you pull over, it cools down, you move on. Maybe a small repair, maybe nothing at all. That's not what overheating is. Overheating is a cascade. Your engine is engineered to run hot, 95 to 220 degrees Fahrenheit is normal operating range. That heat isn't a side effect, nor is the point. Combustion efficiency depends on high temperatures. Your engine is essentially a controlled explosion happening thousands of times per minute, and the entire cooling system exists to keep that explosion from consuming itself. The tolerances are almost absurdly tight, just 15 to 20 degrees above normal operating temperature and aluminum. The material in your cylinder head begins to warp, not melt, warp. That distinction matters enormously, as you'll see. Before modern pressurized cooling systems existed, this was simply accepted as the cost of driving. Early 20th century motorists stopped constantly to let engines breathe. They topped radiators with plain tap water, not knowing that the mineral ions in that water were slowly corroding the system, clogging radiator tubes from the inside out. Roadside steam clouds were ordinary. The problem wasn't a lack of effort. It was a fundamental physics problem that took engineers decades to properly solve. Here's how the cascade unfolds, step by step. It starts with the coolant. Your cooling system isn't just filled with water. It's pressurized deliberately to push the boiling point from 212 degrees all the way up to around 260 degrees Fahrenheit. That pressurization is your first line of defense. It buys the engine headroom. When that pressure drops, from a failing radiator cap, a cracked hose, low coolant, the boiling point crashes back down. Now your coolant is flashing to steam at temperatures the engine was designed to handle as liquid. Steam doesn't carry heat the way liquid does. The engine's ability to shed heat collapses almost instantly. Temperatures spike. And now the geometry of your engine becomes the enemy. Your cylinder head is aluminum. Your engine block beneath it is cast iron. These two materials expand at very different rates. Aluminum expands at roughly double the rate of cast iron. Under normal temperatures, this difference is engineered into the tolerances. Under overheating conditions, the aluminum head tries to grow faster than the iron block will allow. The head gasket, the seal between them, gets caught in that mismatch. It warps. It fails. Think of it like the seal on a pressure cooker lid. The moment that seal deforms, everything that was engineered to stay separated starts to cross over. Combustion gases blast into the coolant passages. Coolant seeps into the oil. The result is an emulsified, milky sludge that can no longer lubricate a single moving part in your engine. Oil that becomes coolant becomes useless. Bearings run dry. Components grind. In severe cases, if you keep driving, piston temperatures climb past 400 degrees Fahrenheit. The aluminum pistons expand faster than the steel cylinders can accommodate. The piston material is literally smeared onto the cylinder walls. That's seizure. That's not a repair. That's a replacement. The entire sequence from boiling coolant to seized engine can unfold in minutes. It's less like a single failure and more like a circuit breaker panel, where one trip breaker dumps its load onto the next and the next until there's nothing left to trip. That same cascade, thermal runaway triggering a chain of compounding failures, turns out to be one of the most universal problems in engineering. Your smartphone knows this. When your phone overheats, its processor throttles itself. It deliberately runs slower to generate less heat. This is exactly what your car's engine control module does when it detects high temperatures, dropping the engine into limp mode and restricting power. The goal in both cases isn't to stop working. It's to avoid destroying itself while still functioning. Performance is sacrificed to preserve survival. Your pressure cooker knows this too. It uses a sealed, pressurized environment to push water's boiling point above its normal threshold. The exact same principle behind your radiator pressure cap. The engineering insight is identical. Raise the phase change boundary so your working fluid stays liquid longer under heat. More headroom, more safety margin. PC enthusiasts who overclock their processors know this intimately. Push a chip past its thermal design limit without adequate cooling, and the failures follow in sequence: throttle, shutdown, permanent damage to solder joints. The repair costs scale with how far you pushed it. Sound familiar? A failed thermostat in your car costs $100 to $300. A seized engine costs $5,000 to $15,000. The gap between those two numbers is the Cascade, and then there's the Spitfire. The iconic World War II fighter used a liquid-cooled piston engine so thermally sensitive that on the ground, pilots had a window of roughly 7 minutes at idle before temperatures climbed to dangerous levels. These aircraft were, in the words of those who flew them, flown by the temperature gauge. Every throttle adjustment was a heat management decision. The same physics, the same trade-offs, the same cascade, just at altitude and 400 miles per hour. None of this is coincidence. It is the same fundamental problem wearing different clothes. How do you extract maximum energy from a thermal process without the process consuming itself? So why not simply engineer engines to run cooler? Remove the risk entirely? Because heat is not incidental. Heat is the mechanism. The hotter the combustion, the more energy you extract from each unit of fuel. Lower combustion temperatures mean lower efficiency, which means more fuel burned for the same output, which means higher costs and higher emissions. Every degree of operating temperature is a deliberate engineering decision, and modern engines are set as hot as possible without crossing the threshold into damage. Electric vehicles face their own version of this. Lithium-ion battery packs generate significant heat during charging and high-demand discharging, push them outside a narrow temperature window, typically between roughly 59 and 113 degrees Fahrenheit for optimal performance. And you see the same pattern: degraded output, accelerated aging, and in extreme cases, thermal runaway. Electric vehicles use sophisticated liquid cooling loops threaded through their battery packs for exactly this reason. The physics of heat management doesn't disappear when you remove the combustion engine. It just moves. The next time you glance at your temperature gauge and the needle sits at its usual spot, you're looking at a small miracle of sustained engineering. Your engine is running hundreds of degrees of controlled heat, held in a precise balance by a pressurized liquid, a thin metal seal, and a thermostat that costs less than a dinner out. Tip that balance. 15 degrees in the wrong direction and the cascade begins. First the coolant, then the gasket, then the oil, then the pistons. $5,000 to $15,000 of damage, initiated by a temperature swing smaller than a hot summer day. Check your coolant level. Replace your thermostat on schedule. Glance at the gauge once in a while. Not because your car needs babysitting, but because now you know what that needle is actually telling you. It's not measuring temperature, it's measuring how close the edge is. And the edge, it turns out, was never very far away.